All right. Hey, so guys, as we're reconnecting with this homework, given that it's been a while since we've been gone for a couple days, let's put this in context. So last time we talked about some foundational things through the lens of what we called the common ion effect, which was basically just Le Chatelier's principle, where we took a weak electrolyte, many times a weak acid, we dumped in a salt that has a shared conjugate base ion, and we talked about how Le Chatelier's principle says it shifts the equilibrium to the left, and we learned all about stuff we already knew relative to Le Chatelier's principle, and then we called time out and we said, that's a buffer. And then we talked about the idea that regardless of what your college professors try to do to you about making you represent buffer chemistry by writing everything out on the same line, you guys are going to dig in your heels and you're going to go, no, I'm going to do this the way Knappenberger taught me because it's better and it works and it's more simplified. And then we started talking about how buffers respond when we attack them with strong acids and bases. You may remember that we talked about the idea that buffers are magic because you can dump an acid or a base into a buffer and the pH doesn't change very much until it breaks. And we're going to talk about breaking buffers in just a minute. But guys, we talked about the concepts behind how buffers respond. We did not talk about the math of how buffers respond. And that's another thing we're going to do today when we talk about I-race boxes. Oh yeah, my very own creation. What do you need to talk about here, y'all? Yeah? Okay. Number one, go ahead. We need to look at a picture, don't we? I sometimes find these pictures very confusing. Okay, so it says the following boxes represent aqueous solutions containing a weak acid, which is them stuck together, and the conjugate base, X minus. Water molecules, hydronium ions, and cations, those being the hydrogens, are gone. Which solution has the highest pH? Okay, so I need to sort of pencil this through, and maybe the penciling through will be helpful. So we've got HX, and this is weak, and then we've got X minus, and then I know they're saying we don't look at H plus, but I kind of need to anyway. So it says highest pH, right? So highest pH means the lowest concentration of this. So that would be the solution that is most shifted to the left. Am I thinking about this correctly? Okay. So how does that then lead us to an answer? So looking at the box on the left, it looks like we've got equal numbers of reactant and product. Looking at the one in the middle, it looks to me like we've got a whole lot more conjugate base. And then looking at the one on the right, is it equal numbers again, but just more of each? So I'm going with the one in the middle. Would you buy that? And was it really that question of highest pH means? Yeah. Well, and yeah. And I'm full on a picture drawer, right? I mean, anytime I sit down to these AP questions, I'm like, crap, I don't know what to do. And you guys know how we've talked about this, right? Guys, that if your response when you sit down and don't know what to do is to freeze up, that's what you're going to do on the test. So my nervous response to not knowing what to do is to draw beakers. If you notice, I'm always drawing. It's because you've got to get pictures in front of you, or in this case, balanced equations. So guys, what else on the homework do y'all need to talk about? Yeah? That's all right. Beautiful. So that's actually where I want to start. So before we get into the new material, I'm going to ask you to do that in your notes. Could we couch that until we do that? Is that okay? Guys, anything else about the homework? Yeah. I have no idea. Sounds like additive volumes, but let's find out. 21. Why did I divide? Oh, why? Oh, yeah. So where did I get this? Guys, please hear this. This is going to be the very crux of iRace boxes. Please. So the idea is this, that we've got a solution that is made of 85 milliliters of lactic acid and then 95 milliliters of whatever this lactate salt is. But when we mix those together, we're not just mixing ions or molecules, we're also mixing water. And so that means that really what we're doing is as we react these together, we're also diluting the solution. So when you add this up, it adds up to 180 milliliters, which is that in liters. So realize that the volumes are additive. So what I've done is I've figured out the number of moles of each, but then I divided by the volumes in order to come up with the molarities of those two components, but the volumes are additive. Is that okay? So guys, please hear this. If you found this bit separated or sort of random, or even where did those volumes come from? Guys, this is actually the math that we're going to put in an iRace box, and it makes it so much easier. So I didn't do it here because we haven't talked about it yet, but iRace will fix a lot of that because it's easier to see. You're going to like it. Guys, what else? You really okay? Oh, yeah. Please. Those are my favorite. Yeah, great question. Great question. So guys, the question on the table is, when do we include water? And the answer is, it's never wrong to include water, but don't if you don't have to. Because we understand that all of this is aqueous chemistry. And when it's acid-base aqueous chemistry, the water is an acid and a base, and it's a component of the reaction. If nothing else, it's a hydrogen ion absorber to make hydronium ion. But that said, it also complicates things. So my advice would be the only time, and again, this is just acid base, right? This doesn't count when we're talking about precipitation reactions or redox reactions or whatever. But in acid-base chemistry, the only time that I include water is when it's a weak base. Because and think through that, you've got to have the water in order for there to be a source of hydroxide, because weak bases turn water into hydroxide. So the water is important to the chemistry. So always include it then. Is that okay? And then remember what we do when we write the icebox, we just squiggle the water, right? Because it doesn't have a molarity, but it's got to be there. Anything else, y'all? Are we good? Okay. So let's do this then. Wait, I got to do this up here. And let me, oh, shoot. Guys, I can't record. Because if I record, I'm about to show the entire world your grades. Oh, can I? Is there a pause? No. Quit it. You guys are so, what's this do? Oh no, we don't want to do that. Well, would you look at that? Par back. Here we go. All right, guys, today we are titrating buffers. Guess what we're going to do in lab? No, not yet. But we will be titrating buffers soon. Okay. So, guys, you tend to be a fairly intuitive group. As a result, I think it would probably make sense to you that if we're going to talk about titrating buffers, that probably relies upon our understanding of buffers. Seems reasonable. So guys, as a result, we are going to go together exactly where Meredith's head went individually. And guys, we are going to start by allowing you the opportunity to really fully get your arms around the function of buffers. Because, and you guys understand this, right? You can build a buffer out of a weak base or a weak acid, right? Don't write this down, but let's just make sure you're okay on this idea. So, guys, we can build a buffer out of ammonia. Please don't write this down. But we can build a buffer out of ammonia. To do that, Matthew, to your point, we've got to have the water, right? Because we're weak base. This reaches equilibrium. Guys, again, we always have been saying conjugate first, right? So if this is our base, this is our conjugate acid. That's the important thing that we're going to look after. So guys, this is just the function of ammonia and water. Here's the $11,000 question. What would we add to this in order to turn it into a buffer? Just a second. Hi, how are you? Good. It's good to see you guys. Come on in. Yeah, so please make yourselves at home. So guys, just so you know where we are, we just got done reviewing homework and talking about the function of buffers. We're reviewing a little bit, and then we're going to start talking about titrating buffers in just a moment. So guys, again, back to the question, and we are, Meredith, going to get to the thing you want to play with, but I think this is worth visiting for a moment. So guys, most of the examples that you're going to see is where we build buffers out of weak acids and conjugate base salts, but we can also build buffers out of weak bases. But then the question is, what are we going to use to buffer this system? So our weak electrolytes, the NH3, right? So where's our common ion going to be? What is the common ion that we're trying to increase the concentration of? The NH4 plus, right? So we need a salt that contains NH4 plus. But notice now the reasoning is backwards compared to what we did previously. So now the ion that we're trying to create, the common ion effect, is now our NH4. And that's the positive ion. So guys, what are we now going to do to turn this into a useful salt to create the buffer? We need a negative ion, but let's be smart about this. Let's pick a negative ion that doesn't muck around with water. There we go. And they're starting to flow, right? Because these will be the negative ions from what? The strong acids. So HCl, HBr, HI, HNO3, H2SO4, ClO3. So any of those would work. So guys, let's just pick our good friend ammonium chloride, and that's how we're going to create the buffer. Does that work? Okay. Now guys, let's do this, and then I want to turn this back to you and let you guys muck around with this. So Meredith, let's do your question now in this context, and then I'm going to have you guys map this out from the start just to reinforce your understandings. So guys, we learned last time that the magic of buffers is that we can dump base or acid into this thing without an appreciable change in pH. But now, guys, where are we going to see what is going to change in this equilibrium that would represent a radical change in pH? It's not protons anymore. What's the thing we're keeping our eye on relative to pH? The hydroxide. It's this guy. And guys, this is where it takes another step in order to solve these, and you're going to see them in homework today, that we're going to end up solving for a POH, and then we go pH plus POH is 14. Okay. But with that said, guys, let's talk. So, who are our players in this buffer? Well, we've got ammonia and we've got ammonium. Guys, those are our buffered pair. That's what we call them. That's our buffered pair. So when we add a strong acid to this, who steps up and takes the bullet? The NH3 or the NH4 plus? Why the NH3? Because the NH4 plus can't, right? Because it's already positive. So guys, that is going to do this. And for every molecule of strong acid we put in, one of these dies, one of these gets created. That establishes new concentrations that then come to equilibrium. But guys, along the way, those hydrogens don't muck around with the OH, and it doesn't change the pH much. Is that jiving with your understandings? It's a little different, isn't it, in the context of a base buffer, but the stuff works the same. So guys, questions there? Okay, so what if we go the other way? What if we add OH? Who's going to take the bullet if we dump in OH? The NH4 plus. And so it goes in this direction, forming this. But guys, again, what's our other product that's going to come out of this? Water, right. So the OH grabs the hydrogen. Water is a side product of that process. But again, these OHs don't increase the concentration of OH appreciably, and the pH doesn't change. So guys, big deep breath. What do you need to talk about relative to buffers? You okay? Okay, so guys, I'm going to stretch you a little bit. In your notes, please do this. Give yourself some space. But we're going to try to do this with a generic representation. So let's go HA, which you guys I hope are comfortable, is a generic representation of an acid, a weak acid in this case. So we're going to do this. And guys, please write in the products of this dissociation. Then we're going to go strong acid, strong base. And guys, please draw in the arrows that represent, the same way we just did on the buffer. Guys, please draw in the arrows that allow us to think about how the strong acid and strong base are going to interact with this buffered system. Because once we've done this, I think together we can say that we're comfortable with the qualitative function of buffers, and then we're going to get into the math of these things, and we're going to talk about how to break them. We're going to talk about how to intelligently build them, and then we're going to talk about titrating them, and we are going to do I-race boxes. And if you guys can help me figure out a way to monetize I-race boxes, it's a great question. But by the same logic, when you get an amazingly lucrative job based upon the foundation in science that I helped you build, you're also going to share with me, of course. It's got to go both ways. It could come down to chainsaws. In a post-apocalyptic world, chainsaws are going to be important. Oh, yeah. Yeah. Guys, have you had enough time to get done your bit? Okay, so guys, do this. Take the pictures that you drew, share them with the person next to you, see where your differences are, and then fix them. Ethan, did he just abandon you? I got you. Okay, guys, you got 10 seconds. You guys good? Okay, now here's what I want you to do with the person that you're talking to really quickly. Scratch down, this is new, scratch down the identity of the salt that you would use to create this buffer. Do it with the person next to you. What salt are you going to use to buffer this system? It's hypothetical, right? But you can still write it down. What's your salt going to be? I'm hearing the answer. Oh. Okay, guys, my turn. So Guys, what we're going to do is we are now going to use this as our last touch. This is going to be our coming together around the function of buffers that's then going to be our springboard in everything we're going to do today. So, guys, again, and I know you have no frame of reference for this, although maybe our visitors in the back will attest to this. University professors are so good at making this really hard. Guys, again, dig in your heels. Don't give in. Do it like this. It's so much easier. So guys, the first thing that we agreed on, that we are always going to put our conjugate first, and we're going to put our protons or hydroxide second. Guys, the reason that we do that is then we've got the buffer all in one place, and this stuff over here doesn't matter. So we've sort of condensed our system, if you will. So we're going to have our conjugate base, again, hypothetically A minus, and then protons. So then, guys, you understand what we're doing here, right? When we say H plus, we're talking like strong acid, HCl. So the idea is this. When we dump in protons, guys, which one is the sacrificial player? Is it the conjugate base or the weak acid that takes the bullet when we dump in acid? Conjugate base. So this dude grabs this dude. I'm going to do that in red. It just stands out a little better. So guys, what happens is this dude grabs this dude, and it makes HA go up, it makes A minus go down. Now guys, let's make a connection that's going to be really important in just a minute. Guys, this is not an equilibrium process. Let me say that again, because I'm going to ask you why in just a minute. This is not an equilibrium process. This isn't that namby-pamby back and forth stuff. This is qualitative. Because why? Why is it that the process represented in red is quantitative and not equilibrium? Right? Because why is that the case? Go back to what we dumped in. Because what is this? What does that represent? A strong acid. And guys, that's the point. Strong acids don't play this equilibrium game. Strong acids come in and kick trash. Right? They seriously, it's no messing around. And guys, literally, this math is quantitative. For every molecule of this that we add, we are adding we're adding one proton. Guys, for every proton that we add, one of these dies and one of these gets created. That math, you're going to find out, is counting. Guys, literally, one in, one dead, one made. Another in, another dead, another made. It's counting. And guys, what units do we count in chemistry? In moles. Guys, this is the top end of the I-race box, and this is always done in moles. Your university professors are going to have you do that in a separate box. Don't do that. But guys, this calculation is done in moles because that's a strong acid and this is quantitative. It's none of this equilibrium garbage. It's full on, this acid's coming in and kicking tail. Okay? So guys, what about the other one? If we add OH, who takes the bullet? The HA or the A minus? The HA. So this pulls off a hydrogen. If this is helpful for you, water gets kicked out the back end, and it's like this. But guys, now we're talking about the addition of a strong base like sodium hydroxide, and this is strong. Whoa, this is, what did I do? Did I hit pause again? No, I'm still going, right? Oh, good. Okay. So, guys, this is strong. It doesn't do equilibrium. This is butt kicking. So this thing comes in, and a hydroxide, every hydroxide that goes in, a hydrogen comes out. One of these dies, one of these gets made. Again, guys, the addition of the strong acid and base is quantitative moles-based chemistry. What questions do you have before we build on this together? You guys, yeah, please. Yeah, and Matthew asked a similar question last time we were together. The reason is because it's always looking for the easiest target. And the easiest place to get your hydrogens is from the weak base, or the weak acid. So we're always going to attack, like the wolf in the deer herd, right? It's always going to pick on the easiest guy to attack. What else, y'all? You guys good? We're sitting okay? We're feeling good about this? Okay, so guys, let me then lay out the rest of the day for you. The first thing that we're going to do is we're going to talk about how to build buffers. It's qualitative. It's stuff you're going to see in multiple choice. So guys, we're going to talk about how to build buffers and then also when do buffers break. Then after that, we're going to start doing this and we're going to do the math of titrating buffers. You guys ready to go? Okay. So guys, first things first, bink, bump, boom, and hey, there we go. Okay, so guys, it goes like this. Be judicious in the things that you write down. But guys, when we talk about buffers, there are two important things for us to talk about. It's going to draw on some of the math that we did last time, but you only need to be able to talk about this. So it's at least worth writing down the two characteristics that we need to keep track of. And guys, those are, first of all, capacity. So guys, when we talk about capacity, we're talking about the amount of acid or base that a buffer can absorb before it blows up and dies. Because guys, this doesn't go on forever. Eventually, you are going to run out of sacrificial particles, whether that's the weak acid or the conjugate base or whatever. Because eventually you run out. And when you're done, you're done. And we're going to do this in lab, and we're going to watch the titration curve, and it all of a sudden goes bing, and it's all over. So guys, when we talk about capacity, we talk about how much can this absorb. Well guys, that is a function of how much weak electrolyte and salt you make the buffer from. Guys, this brings up a really, really interesting bit that's going to relate back to the math that we learned last time, but you're not ready to learn it because you're still writing stuff down. Was it Mark Twain that said, don't let your education get in the way of your learning? Oh, it's not. No, education has nothing to do with learning. It has to do with getting 16-year-olds to put their butt in the same place for 80 minutes at a time. Wait, did I just say that? My bad. All right, you guys good? Y'all caught up? Okay, so guys, let me, this may be too much and it's going to steal the magic a little bit. But guys, do you remember when we figured out the pH of buffers and all of a sudden stuff just started canceling? Do you remember? So the X's canceled because they were insignificant. And then why did the molarities cancel? Because they were the same. So guys, based on that, no pun intended, please don't write this down. Please don't write this down, but here's the question. Just don't write it down. Just read. So you take a 1 liter solution that is 1 mole of acetic acid and 1 mole of sodium acetate. That's our buffered pair, right? Then imagine that you have a 1 liter solution that's 0.01 molar in the same buffered system. Here's the interesting question. How many more, this isn't the interesting question, but it's foundational. Guys, how many times more concentrated is the top solution than the bottom? 100, right? So it's 1 molar versus 100th molar. It's 100 times more concentrated. Here's my question to you. What are the pHs of these two solutions? They're the same. And guys, let's talk about why. How do we actually figure out the pHs? We got to do the ice box. But can you picture the ice box where we've got the weak acid and we've got the conjugate base and their molarities are the same? So when we get down to the Ka value, this molarity cancels with this molarity cancels with this. And then guys, the X's drop out, plus and minus, because they're insignificant compared to the initial concentration. Everything cancels out. And what are we left with? Ka. And what did we then find pH was equal to? You better know this. pH is equal to pKa. Remember that? So guys, what will the pH of both of these solutions be? pKa. Guys, understand that this only works when these molarities are the same and these molarities are the same, but they are, and pH is equal to pKa. Now here's the tricky bit. While these have the same pHs, which one is a better buffer, top or bottom? Which one's a better, well, what do buffers do? They absorb acids and bases without appreciable change in pH, right? So which one's going to be a better acid or base absorber, top or bottom? How many times better? 100 times better. Do you get the idea? So guys, that's what capacity is all about. If we make these equal molar, then pH is pKa, but if we use more, we get a better buffer. Make sense? Okay. So guys, the other one then that we need to talk about is pH range. You're going to see this in multiple choice on the AP test. So guys, pH range is the range around which a buffer will be effective. We may not have time to do this in third period. Thank you, COVID. But guys, what we'll do many times, and it's really fun to watch, I turn my AP kids loose in the stockroom, and I just set out some weak acids, like acetic acid and lactic acid and formic acid and things like that. By the way, guys, what form will those acids all be in before they're dissolved in water? They're salts. They're crystalline. They're not salts. They're molecular, but they're molecular solids. They all look like salt, but they're not salts. They're crystalline solids. And guys, I'll say, all right, guys, we're going to build a buffer that has a pH of 4. Go. And you then have to decide which weak acid are you going to use. So guys, the question is, how do you know which one to use? We probably won't have time to do this year, but you do need to understand the concept. And guys, the answer is this. Buffers are most effective when the concentration of their weak electrolyte and the conjugate are about the same. And guys, I know that for many of you, those are just words. So let's turn these words into something that we can understand. So the idea here is that when we're building buffers, better built buffers, I know, right? Better built buffers have as close to equal concentrations as they can. So what that means is coming back to our previous example, if we have HA and A- in protons, better buffers have approximately equal concentrations of our buffered pair. The beauty is that it actually makes the math easier, because if they are the same, then pH is pKa and life got really easy. But guys, this actually makes better buffers when these concentrations are about the same. Now we understand that when that's true, pH is, drawing dots. We understand that when that's true, pH is equal to pKa, right? So if we've got approximately equal concentrations of HA and then our A-, if those are approximately equal, then pH is pretty close to pKa. So guys, given that information, question. We've been using acetic acid as our foundation for buffers just because we're all familiar with it. Here's the question. If you had to start from scratch, grab your calculators. If you had to start from scratch, and if you had to build a buffer, what pH would acetic acid be a good choice to build your buffer out of? Did that make any sense at all? That barely sounded like English to me. So, but the idea is this, guys. If we're building a buffer, and if they give us acetic acid and then sodium acetate to build our buffer, what pH would that be a reasonable choice to build the buffer for? Was that any better? What do you need to know? You need to know Ka. Sadly, some of you have it memorized as well. It's 1.8 times 10 to the negative fifth. Sadly, I know the negative log of this. My mind is full of worthless information. 4.74? Can you verify that? Yeah. Crazy, right? So, guys, That's the answer to the question. So if we're going to build an acetic acid buffer, we're going to add as much as we can, right? Because that's capacity. So we're going to make 10 molar vinegar with 10 molar sodium acetate. Now we have a huge buffering capacity. But guys, when we do, its pH is pKa, it's 4.74. So if we wanted to build a buffer with pH 9, that's a stupid choice. Could we get it to pH 9? Yeah, but then our concentrations would be so out of whack that it wouldn't be a good buffer. You see what we're saying? So here then becomes the question. How far can we push this before we've just made a buffer that's not effective because the concentrations are so different? And guys, the answer is this. It's plus or minus 1 pH step. Now guys, do this with me. We're talking about logarithms, right? So what number is represented by a plus 1 change? That's 10 to the first, which is 10. Guys, what number is represented by a negative 1 change? A tenth. So guys, what that means is we can have a concentration gradient that could be 10 times higher or 10 times lower in terms of that ratio of weak electrolyte to conjugate salt. If we can stay within about 10, within about a power of 10 molarity in either direction, we're still pretty good. Anything beyond that, and our molarities are so out of whack that it's no longer effective. So fundamentally, guys, here's what you need to know. If you're building buffers, figure out what pH you're shooting for. pH is pKa. Make your buffers with equal molarities, and then find your weak electrolyte that has a pKa as close to the pH as you're looking for. That was a lot of information. What do we need to talk about? You guys okay? Yeah, Ronnie. Well, yeah, but you'd have to go to Appendix D or something like this, because it's actually not stamped on the bottles. And to be, well, so that's what you would do is you would need a Ka chart. And then really, if you're really lucky, you need a pKa chart. And then you just let your eye scan down the pKa chart and you find that acid that has the pKa that's approximately the pH you're looking for. And then you just go equal molar amounts. Yeah, so what you might see on the AP test, now that you can use calculators in the multiple choice, they might give you like 3 weak acids and then conjugate salts and give you the Kas, and you just really quick create the pKas for those 3 things and then just find the one that matches. And as a matter of fact, a lot of times the Kas are going to be simple numbers like 1 times 10 to the negative 5th. Oh, that's 5. So they sometimes simplify for you. What else, y'all? You good? You ready for the iRace box? Here we go. So guys, we are now going to start titrating buffers. We're done with that. You're good with this idea of about 1/10 to, we're good. All right, go. Here we go. Guys, titrating buffers. Shoot. I should have just printed this for you. Let's do this. Let's let the first half of this be conversational. And then the last part of this, guys, I really believe is going to be worth writing down, at least in part. Okay? So, guys, I really don't need to mention to you what I'm about to share with you, but technically I have to, because when you get into college, you're going to find examples of when this isn't true. So, what we're going to do is this. We are now going to look quantitatively, the math, right? We're going to look quantitatively at how buffers respond to the addition of strong acids and bases. So the pictures that we drew here, we're now going to do the math that describes this, okay? But guys, maybe this would be a good time to mention this. We've actually got 2 things going on here. And guys, this is how we're going to think about this. Guys, what we've got going on here is we have got the equilibrium, we've got our buffer, and then the first thing that we've got is the butt kicking that happens when the strong acid or strong base comes in and attacks the buffer. Okay, so that's going to be process number one. This overwhelming thing that happens. Just a second. When the acid or base attacks the buffer, then once the attack is over, we're going to have the equilibrium that's reestablished as the new concentrations of our buffered pair then establish a new equilibrium. So guys, that's how we're going to talk about this. We're going to talk about butt kicking, and then we're going to talk about equilibrium. We're going to put those together in an I-race box. Again, in college, many professors ask you to separate these. Don't. And I give you Mr. Coxon. He's a good-looking guy, don't you think? I mean, just empirically. What's up?
I just had to let you know that you can now become part of Team March.
No. So you need the backstory. So you guys know I cycle. And we have this strange little dysfunctional cycling group here at the high school that used to ride with us, Annika. Yeah. And then with COVID, we could no longer have the students join us to ride because of social distancing reasons. But as adults, we continued to train. And now Mr. Coxon and several others here at the school have committed to ride their first century, their first 100-mile ride this summer. And so we are now training as a group to ride a century up in Cache Valley. But what's that? I mean, this sounds, I don't keep count of how many I've done a lot. Yeah. So, yeah. So yes, I've ridden lots of centuries. But it's a big deal. And so this year, yeah, we have time. Okay. So this year what happened was they have to give you start times because normally they're mass start, but with social distancing, you have to start, they give you a time. But if you want to start with your friends, you have to become a team. And this year I'm not riding with my team. I'm actually riding with this high school group. So we needed a name. So I have a friend that I ski with a lot. And at the end of the ski day, we'll be in the parking lot, sort of wrapping up the day, and you just know it's coming. His name is Sid, and Sid will look around and he'll go, "Great snow, man, good snow day, and amazing weather. Oh, the weather was unbelievable, and marginal company. It's been a pretty good day." So, and that's his deal. It's great snow, good weather. And so we've adopted that. So it's great roads, wonderful weather, marginal company. So the name of our team is Marginal Company. And yeah, so there you go. So you created the team.
It's ready to go.
Good.
Hop on board and go out.
All right. I love it. Now we just need to print jerseys. Yeah. I love it. All right. There we go. So, guys, are we ready to now turn this into math? Say yes, because if you're not, we're going to do it anyway. All right. So, guys, it goes like this. So, don't write this down, but, guys, we do need to talk about this. In order for us to do this, the first one is obvious, and the second one, honestly, is a godsend. So, guys, it goes like this. These are the two assumptions that we need to make. So guys, first of all, we need to assume that we haven't broken the buffer. The buffer still has enough of one of those two buffered pairs that it's still being a buffer. But then guys, the second assumption that we have to make is this. The acid or base that we are adding reacts completely with the buffer. What does that tell us about the acid or base? It's strong. Thank goodness. Because guys, if we had to figure out how weak acids and bases deal with buffers, now we have competing equilibria. Now we're talking about calculus. And we don't have to do that. No, he'll be fine. No, because he's now teaching physics and he's finding that math in the science domain is not as fun as he thought it was in his world. That's actually not true. Don't tell him I said that. But guys, strong acids and bases. You do not need to worry yourself about adding weak acids and bases to buffers. I don't even remember have you guys done that? Weak acids and bases into buffers? I don't even remember that in PChem. Yeah, it's yucky. So, guys, anyway, we're going to keep this simple. How are we going to do it? You guys are going to write this down with me. It's strong, thank goodness. So, guys, this becomes a two-step problem-solving process. I may not be able to monetize this, but you can turn this into an amazing dating opportunity in college. Because while missionary dating is always a no-no, academic dating is always a good idea. So, guys, when you get to your chemistry classes, you're going to see your classmates struggling with this because of the way they were taught it, and you just go, why don't we get together tonight and let me show you? Oh, yeah. Throw on the Barry White. You're ready to go. So, guys, it goes like this. This is what is called the I-race process. Step number 1. Do write this down. Step number 1 is the acid-base neutralization. And, guys, we've already established that this is strong. This is not equilibrium. This is quantitative. This is a strong acid or base ripping the bajinkers out of this buffer. 1 in, 1 dead. It's literally body counts here, you guys. And consequently, these calculations are done in moles. And Matthew, this is where it's going to become important, that additive volume thing, because we're going to be converting back to molarity, and we've got to keep track of how the volumes add up. Then, guys, step number 2 is we use the Ka and the newly adjusted don't write this down. But guys, here's what we're going to do. Basically what this is saying is we're going to shift our thinking. We have looked at the destruction done by the strong component, the strong invader. And then, guys, we're going to shift our thinking, and now we're going to go, okay, what did that acid or base do to that equilibrium system? Then we're going to start again there. We're going to switch our thinking to equilibrium, and we're going to do adjusted, changed, and equilibrium. You guys, do write that down. But it is important that you understand that these are molarity calculations now. So the beginning of this is in moles because it's strong. It's not equilibrium. It's not rate dependent, right? 1 in, 1 dead. But then when we start talking about equilibrium, guys, we understand equilibrium is all about forward and reverse rates, and rates are a function of molarity. So we've got to shift mathematical gears and start thinking about molarity. And it's at that point that we've got to divide by volume, convert to molarity, and then it's just an icebox. Okay? Okay. So guys, we're going to solve one in the next 20 minutes, and then you're going to have some time to practice. You ready to go? So guys, if you've gotten to the bottom of your page and you're like you need a big old place. Okay, y'all, don't write this down, but read it. It says you make a buffer. You make a buffer by mixing 100 milliliters of acetic acid, 1 molar, and 100 milliliters of 100 milliliters of 1 molar sodium acetate. They give us the Ka, and then the question is this. Calculate the pH after, and the one that we're going to look at first is adding 50 milliliters of HCl. So guys, let's set the stage for this first. First of all, what do you notice about the molarities of the buffered pair? They're the same. So what is pH? pKa. You good on that? Okay. Now guys, notice this. The thing that we are adding is strong. Will it always be? Yes. So guys, this then is what we need to do. We know that for every molecule of HCl that we add, something's going to die and something's going to get created. Can you picture the arrows as we're thinking of buffers? So guys, in order for us to think about that, we need to know how many particles of both the weak acid and the conjugate base, how many particles of those do we have? So to do that, we need to do some dimensional analysis. Guys, this is a back of napkin calculation, but it is something the AP graders expect you to represent. I'm going to do it. You just do it. So guys, we've got 100 milliliters of our acid. 1,000 milliliters is 1 liter. 1 liter is 1 mole. Oh, look at me choosing easy numbers. This is math that even I can do. 0.1 moles of, we'll write it out. And we should probably, let's allow ourselves a little freedom with significant digits because, frankly, this is sloppy. We would have measured that volume better than to one significant digit, but we'll play with it. So then, guys, we need to know how much conjugate we added. So still same, yeah. Hey. Groovy? Y'all good? Did I do anything stupid yet? I hope the person that grades your AP test uses as fine a pencil as you're expecting of me. Judge not, lest ye be judged. Are we good? Okay, so now, guys, this is where just put those numbers in your back pocket. And now it's time to get to work. So, guys, the magic, and please don't get ahead of me. Structure here is going to be very important. So, again, we're going to start just like before. Let's set up our buffer. I'm going to do it in red. So we've got we're going to need a finer pencil. CH3, COOH. Don't like that either. Just a second. I'm going to need a little room to write up above. CH3, COOH. In equilibrium, we've agreed that we're going to do this and then this, like so. Starting to feel familiar, right? Now, guys, watch before you do. You have the advantages of having lines on the paper. I don't, so bear with me. But here's what we're going to do. We're going to go I and R, then skip a space. Then A, C, E. Now, guys, we are going to be maybe a little sloppy with significant digits, but we are not going to be sloppy with units. It's critical to your understanding. So, guys, the first thing that we are going to describe is the neutralization. Neutralization is all about, in this case, strong acid, right? HCl, yeah, is all about a strong acid ripping this buffer apart. That's the neutralization we're talking about, and that has to happen in moles. And then, guys, once that's over, we are then talking about the newly reestablished equilibrium, and that happens in molarity units. So, guys, let's talk about where this buffer starts. So, rereading what we were told initially, we know that we've got 100 milliliters of 1 molar acetic acid, 100 milliliters of 1 molar sodium acetate. We converted that to moles. So we now know, and guys, again, sloppy with units, right? Oh, I want to switch to blue. So guys, we know that we've got 0.1 moles of this, we've got 0.1 moles of this, and we have none of that yet. Are we good? Okay. Now, guys, we have one more background calculation that we need to do. I didn't want to do it at first because I was afraid it would be distracting, but we need to do it now. I would do it off to the side because, guys, the question is this. Here, let me bring us to the thing. So we are adding HCl, right? So let's then go back here to our picture and let's add that to our picture. So you understand how we represent this. We do it by drawing an arrow. Will that arrow go to the left or to the right? Frighteningly, I actually did that correct, didn't I? To the left or the right, but this is my right. Come on. So guys, will that arrow go to the left or to the right? It's going to go to the left, right? So you were doing it backwards too. Does that fit okay? Guys, please do take the time to draw this in. I cannot wait to get the emails from you guys next year. You'll be on missions. But. Okay, so guys, what does that mean? What that means, notice the logic behind this one. What that means is that when we have acid, one of the eyes grabs this, turn it into that. So guys, what's going to happen? The amount of this up or down. What's going to happen? The amount of this. How much will go up and down? What's the answer to that question? How much? Again. How much you put in of the acid? So now we need to go back and look at that, don't we? So guys, if we go back here, how much acid are we adding? We're adding this much. But we need that not in molarity units, but we need it in moles. So we're going to go 50. Ronnie, watch. Oh, I did it again. $1,000. So is this 0.05? That's math I can't do. It is, right? 50. I know, but that involves logic. Yeah, 0.05. Okay. So guys, let's make sure you're really clear on what we just figured out. We now know how many particles of HCl we added. In moles, but those are counting groups. So we know how many moles of HCl we added. Let's take that information and bring it over here. So we are adding 0.05 moles of HCl. So we are going to react up 0.05 moles and 0.05 moles, and this ain't going to change. Now what we've got to do is put signs on it. So is this a plus or a minus? Follow your arrows, you all, if you're not sure. Is this going up or down? It's going up. So this is plus, this is minus. Now we can do that math. So this is 0.15 moles. And yeah, that's what your empty space is for. And this is 0.05 moles. And this is still 0. So now, guys, here's what we know. When the carnage is over from adding the acid, this went up by the amount of acid that we added. This went down by the amount of acid that we added. So now, guys, once the war is over, this buffered system then goes, okay, time to go back to equilibrium. But as we move back to equilibrium, we're now talking about equilibrium processes which need what kind of units? Molarity, because they're rate dependent, right? So now we need to convert back to molarity. To do that, we divide by volume. Matthew, this is where these additive volumes become important, because guys, now look what's sitting in our Erlenmeyer flask. We've got 100 milliliters of this, we've got 100 milliliters of this, and we've got 50 milliliters of that. What's our total volume? In liters, divided by 0.25, and divided by 0.25. Did that make sense? So guys, I get 0.6. Is that okay? And then 0.05, 0.2? 0.2? But guys, are you keeping your eye on that right-hand column? Have you noticed that hasn't changed? Why do we care that that hasn't changed? Because that's pH, right? Now it's going to change. So now let's do this. How does this fall to equilibrium? Just like before. This goes down by X. This goes up by X. This is X. Now it starts to feel familiar. So then, guys, this would be 0.6 minus X. This is 0.2 plus X. And this is X. Now, guys, at this point we need to talk. On your equation sheet, there is an equation. Don't look. On your equation sheet, there is an equation that will allow you to solve this just flat out. It's called the Henderson-Hasselbalch equation. This was a part of the AP curriculum for decades. Then they took it away. That was the best day in my life because I'd never taught it, because why cheat when you can understand the math? But guys, then they brought it back. I didn't even know they brought it back. My son told me. He's like, yeah, it's back. I'm like, I didn't even know. If you want to use Henderson-Hasselbalch, you can, but I strongly encourage against it. Because, guys, all Henderson-Hasselbalch is a condensing of what we're about to do together. So let's do it together. So, guys, we've got Ka is equal to CH3 COO minus and protons and CH3 COOH. And Ka is 1.8 times 10 to the negative fifth, and that would be equal to 0.20 plus X times X divided by 0.60 minus X. Did I do that right? It feels weird. Yeah? Okay. So now, guys, what can we cancel? What's our approximately equal to? Let me not do that math quite yet. What cancels? The plus and minus X, right? These guys are gone because they're insignificant. And then, guys, we can do this math. So we end up with X over 0.3. Yeah? Oh, gosh, thank you. Pretend that point's not there. Thank you, Spencer. So X over 3. And then, guys, we solve that. So we have 1.8 times 10 to the negative fifth. Multiply that by 3. And, guys, that gives me, let's do this in scientific notation. I get 5.4 times 10 to the negative fifth. So guys, that is our concentration of hydrogen ion. Then forgive me for not doing, we should write this out, pH is equal to the negative log of, but let's just take the negative log of that. We've played that game enough. And guys, I get 4.27. That will then be the pH of the buffer. Now here's the hazard. You look at this and you're like, great. But guys, remind yourself, where did this buffer start? 4.74. pH is pKa, right? This thing started at 4.74. So guys, its pH only went down, therefore more acidic, right? Its pH only went down by half a pH step. And guys, look at what we added to this poor buffer. We nailed it with 50 milliliters of ridiculously strong hydrochloric acid. You dump that into water, it's game over. But you dump that into a buffer and the pH barely nudged. That's the magic of buffers. Which brings us to an interesting follow-up question. What if we did this? What if we added sodium hydroxide? You guys ready? Play along. Right, but what if we just changed this? Guys, it was 50 milliliters, same amount. Let's look. It was 50 milliliters of 1 molar sodium hydroxide. Chandler, what's going to happen? Good. Guys, that's all that's going to happen if we go over here. This is OH. So which direction now is the arrow going to go? To the right. And the only thing that changes then is this plus becomes a minus, and this minus becomes a plus, and then you just keep going. Or if we could figure out this difference, which again is math way beyond me, and then just add it to 4.74, that's going to be the answer. Huh? Come on. That's not bad. So guys, that's it. So again, I erase boxes. Thoughts or questions or things you'd like to explore? Please. What I did is these canceled. Spencer saved my bacon and reminded me that 0.2 divided by 0.6 is 3. And then it was just 3 times 1.8 times 10 to the negative 5th. Is that okay? Yeah, I know there's a lot of schmuggle in the middle, but it's just cross multiply. And then you do the negative. Yeah, so then we took that number and we went pH is equal to the negative log and went from there. Yep. Anything else, y'all? All right. Let's do these for next time. And guys, we are going to take a break in what's probably like 7. Come on. We'll see, but we're going to meet here, guys, before we go to lab. So go, come back. See you in a minute.